Okay, so we're looking at problem 2.46. Tells the egg is thrown nearly vertically upward from a point near the cornice of a tall building. It just misses the cornice on the way down and passes the point 50. So let's take a look at what that means. So they're standing maybe. Okay, so here's our tall building. It's thrown from here. It goes up and it just goes down that way. Okay, and it says it passes a point. So it starts here and it gets to a point that they say is like 50 meters below here. And if this point over here is t equals 0, then this point right here is t equals 5 seconds. Okay. All right. They say error resistance can be ignored. And then they ask us, what's the initial speed of the egg? So I'm looking at the initial things I know. I don't know the initial velocity, but I'd sure like to. In fact, that's what it asks for. I don't know the final velocity. I don't know. I do know the displacement of it. I know that the initial y I'm going to call 0, and I'm going to call the final y negative 50. You could call that whatever you want. You call that 50 and 0 if that makes you happy, but I just chose those two. I know that the acceleration is going to be negative 9.8 meters per second squared. This is 50 meters. I got to keep that in mind too. And the time that it takes to happen is 5.0 seconds. Okay. So if I look at all that stuff, I need an equation that doesn't have final velocity in it, but has everything else. It seems like my best candidate is going to be y minus y naught equals v naught t plus 1 half a t squared. So I'm going to have 0 minus 50 equals v naught times 5 plus 1 half negative 9.8 times 5 squared. Whoops, I lost that guy there. Okay. Then I'll take out the calculator here and let's see what we can do with that bad boy. So I've got negative 50 equals 5v naught. Okay, I've got negative 4.9 times 25 it looks like. You can hear me push the buttons. So I have negative 122.5 when I calculate all that together. Bring it to the other side. So I've got negative 72.5 equals 5v naught. Divide both sides by 5, or negative 5, don't I? No, I have 5. Oh, no, I have positive now because I brought that over to the other side. Good. So, which I like because I should have a positive velocity. So I divide that by 5. I get 14.5 meters per second. And again, that's part A that it asked me for there too. Next, we're going to work on part B. How high does it rise above that point? Well, now we've got really all the stuff we need because we know the initial velocity now is 14.5 meters per second. At this top point, again, the velocity is going to be 0, and we know that the acceleration, because gravity is, the air resistance is negligible, we know it's 9.8 meters per second squared. So we can find out what the height is by using v squared equals v naught squared plus 2a y minus y naught. And I'm going to call y naught equals 0, same as I did before. So I'm going to have 0 squared equals 14 meters per second quantity squared plus 2 negative 9.8 meters per second squared. And just y, because y minus 0 is going to give me that. So I'm going to have basically, I'm going to have what is it? 1, 0 equals 196 meters squared per second squared minus 19.6 meters per second squared times y. So I'm going to take a 96 and I'm going to divide it by 19.6. That's pretty easy. I'm going to end up with 20.0 meters for the height that it reached before it turned back around. C and D here are actually pretty easy. It says, what's the magnitude of velocity at the highest point? Well, we know that it's going from having a positive velocity up to a negative velocity down. Let me sketch that again. Okay. So it's going from a positive velocity up to a negative velocity down as it goes past that, as it changes its direction. So we know that that velocity is 0. That's for C. Okay. And for D, it says, what's the magnitude and direction of the acceleration at its highest point? Well, they always try to trick you, and this is a common one. You probably remember it from the past. The acceleration due to gravity is always going to be the same no matter what. It's going to be negative 9.8 meters per second squared. Okay. Then they ask you to draw some acceleration, velocity, and position graphs of the motion of the egg. Well, let's start with the acceleration graph because it's the easiest one to draw. A sub y and t. Well, again, it's going to be negative 9.8 the whole time. So, I mean, it's not going to be hard to say, all right, well, that one's just going to be like that. Negative 9.8, right? Okay. And for the velocity graph, that one's also not going to be terrible to draw either. We know it's going to start with a velocity up here of, at the top, of about, what do we calculate to be, 14.5. And then it's going to drop over time. And because it's a constant acceleration, our change in velocity is going to be constant. Okay. This is the point where it turns around at that maximum height over here. And then this is the point on the bottom. So over here, let me highlight that. Okay. This is all the point where it's actually going and going back down, the point that's over here. All right. And in terms of the position versus time graph, that's the one that's, I guess, the most interesting. Okay. Again, I'm going to call y equals 0 the top of that thing. I mean, really, but the path looks almost exactly the same as what the trajectory looks like. It's going to go up versus time. It's going to go back down. It's going to curve this way. Okay. So the part that we are showing, and it should be more symmetric than what I drew, on the top, above that y equals 0 axis, that's the part where it's above that top of the building. The part below it, which I didn't sketch very well because I ran out of room, is the part where it's actually below that cornice of the building, below the top, and it's heading toward the bottom. That actually should take up the majority of the graph, and it should get steeper and steeper as it goes because the velocity is getting greater and greater because the acceleration remains constant.